Hello everyone, welcome to another session on the machine learning series. Today we'll continue with logistic regression. In the previous few sessions, right, we are discussing on what is logistic regression. We are trying to understand what is logistic regression, how it actually differs with that of linear regression. We are also looking at what is the hypothesis function of a logistic regression, what is the cost function, right, and how do you actually take out the derivative of your sigmoid function. Right. We are also looking at what basically is general form of gradient descent and how is gradient descent applied specifically in case of logistic regression. So today we will just continue with that. So in previous session it was more of theoretical, right? We were looking at more from a theoretical aspect. But we will walk through code, right? So as to even solidify our understanding, right? So this is what is, say, we'll just read a sample file. So right, so in this what is the main objective is to predict whether a particular student will pass or not pass. Like, this is a number of hours you study and this is number of hours it's left. And so this is a typical case of a binary classification problem. So in classification problem there are many types of classification problems, right? So you could have something which is called as a binary classification problem, right? So what is a binary classification problem is you have only two categories in your response variable, right? Consider the same case where you're supposed to say whether he has passed, right? Whether this particular student or individual has passed or not passed. And so this is an example of a binary classification problem. An example of a multi-class classification problem could be, actually, you're shown a picture of an animal. You're supposed to be whether it's a cat or a dog or a mouse or whatever. So you have more than one class, right? In your target variable or in your response variable, you basically have more than one class. So that is an example of multi-class classification problem. Okay. So there's actually one more type of classification problem, which is called as multi-label classification problem. So just to give an example, right? So suppose you're watching a movie, right? Consider any movie, right? So when you look at genre of that movie, right? So it is always not the case that it'll only be a genre of only one type, right? So if you consider any movie, right, it could be either action movie, it could be either adventure movie, it could be a comedy movie, a romantic movie. So a single movie could have multiple genres. That is basically an example of multi-label, right? A single movie could have multiple genres, so that is an example of multi-label classification. Coming back to our particular data set of our particular use case, our data set is basically an example of a binary classification problem, right? Because there's only two classes. So coming back, we'll just look at how do you actually. We'll just basically start off with. We'll get back to this. We'll just basically start off with your cost function, right? So in our previous discussions, what we basically saw was the definition of cost function. Definition of cost function is nothing but your log loss or cross entropy. Right? This is binary log loss. Again, it's not your multinomial log loss. That's the binary log loss. And so this is just a predict function. This is nothing but it just takes the normal dot product or a normal multiplication between your feature matrix and your weight matrix, and it finally passes through a sigmoid function. So this is nothing but whatever that overlay we saw, right, where we had three inputs, where we had multiple inputs, and we basically passed that through a sigmoid function to get probabilities. This is basically that. Okay. Coming back to the code on your cost function, right? What is happening inside cost function? So this is, assume this is your features. Your feature vector is nothing but it's a feature vector it's a data frame of say 100 rows and 3 columns. Labels is just 100 rows. You just have either pass or not pass. Your weights, since you have only 3 columns, right? Your intercept, you have one particular weight for your studied and another particular weight for your slept. So it says 1, 2, and so you just have 3 weights, right? So this is what is a binary log loss or cross entropy, you can call it, right? So this is your prediction. This is your y. This is your actual y values, right? This is your predictions. So basically, first what we do is, so log loss, as you can see, when y is equal to 1, it has a certain formula. When y is equal to 0, it has a certain formula, right? When y is equal to 0, it's nothing but 1 minus log of your predicted, right? 1 minus your 1 minus labels, right? 1 minus labels into log of 1 minus predictions. 1 minus labels into log 1 minus predictions is nothing but your, when label is 0. When the label is 1, your formula becomes minus of labels into log of just predictions. Right? You just sum of both of them. So this is your final cost. This is your final cost. Next, what we basically do is now we have a cost function ready. Now we basically go into actually running the gradient descent algorithm. So where we actually update your weights, right? So from the basis of a previous discussion, we know that the derivative of sigmoid is this, right? S of z1 minus z. Now similarly applying same principles of partial derivatives, which we did see in our linear regression example, right? Where we took partial derivative with respect to two weights, applying a very similar concept. Oh yeah, this is what you end up with as the derivative of your cost function, right? Now we again start off with your gradient descent, right? We basically start with the gradient, then we just calculate the update. We just calculate the average of your gradient, and we calculate the update. Right, so this is basically where we just update the weights. Right, initially you would have a certain initial set of weight. You would have assumed a set of weights. From that, you basically update your weights to your gradient descent. Right, so this is where you do your predictions. You're just taking the dot product of your features and weights and passing it through your sigmoid function. And this step is nothing but your very soon step. So this is the first sheet which we discussed in the previous video. If you guys could just recollect. Right? So you had three inputs. You had an input. Yeah, you had an intercept. So whatever was passed, whatever linear form factor was passed to sigmoid function. That is this. Next, you're basically taking your gradient step. Right. So this is nothing but from where are you getting this is nothing but your this. So this is gradient is nothing but your derivative. Right. Then you take the average. Then you do the normal step of where to get an update. What do you do to get an update is gradient minus your this thing. Gradient minus your initial value minus the eliminated gradient. So in case you have followed the gradient descent discussion steps which we saw in linear regression, right, at the very beginning of the series, so if you are comfortable with that, other logic, all of this is similar. Obviously, except you would be changing your derivatives. Over there, it was derivative for cost function for linear regression. Over here, it's derivative of cost function for logistic regression. But other than that, the fundamentals remain the same, right? Next, we basically move on. Say after you get your probabilities, right? So this is being a probability, right? You need to basically convert your probabilities to 1 or either 0. What we basically do is we fix a threshold. So usually by default in algorithm, in libraries like sklearn and other ML machine learning libraries, 0.5 is actually chosen as the default threshold. So if a particular probability of a particular this thing for a particular row is greater than 0.5, it's 1. Then 0.5 is 0. But most of the time, this would not be the case. So depending on your error metric, depending on your metric, you would be either say consider if your metric is either precision or recall. Right? What you would be doing is either you would be varying this threshold. So as to depending on your use case, if your use case is to maximize precision, you would be choosing a threshold that maximizes that. Or if your use case is to maximize recall, you'd be choosing a threshold which will maximize that. Right. So next moving on to your this is where you just do a prediction. You get your probabilities. After you get your probabilities, you sort of run the decision boundary logic over there, right? So this is the code. This is the thing over here. All of this is individual codes, very easy to follow. Now what you can basically do is you can basically package this code into one single class. So this is what usually happens in a logistic regression when you actually look at it in terms of from an sklearn, right? When you actually look at it in sklearn, this is what usually happens. They just package it into a single class, right? So in sklearn, how it is built is sklearn you have classes for each of those. Say if you're trying to run a linear regression algorithm, you have a class. Logistic regression, you have a class. Basically, what you need to do is you just need to instantiate your class, create a model object, right? And on that model object, you can either run your fit method or you can run your predict method. You can run any of these methods. And it's actually this API, right? It's actually consistent across any model. If you want to learn any linear regression, you just need to create a model object. After that, you can just use your fit method, predict method to train or run a predict operation. So going back, so how this has been written is you have a logistic regression class, you have a class for you have a method for sigmoid, you have a method for intercept, method for fit, and you predict. So now to run this, basically what you can do is you can just execute this class and then create an object of this class. Then you should be good to go. So this is easier to follow, easier to understand. But if you're actually planning to go in sort of a prediction mode, right? If actually production mode, or if you're actually trying to implement this, so class is what I would usually suggest because it's far more cleaner to implement and far more easier to maintain as well. So instead of having a set of bunch of unrelated functions, it's always a good idea to just package it in form of a class. Right. So let us running this, you basically, I think you get an error because these values are not basically defined. So you just basically need to define your x and you need to define your y. So that is not defined. Right? This is output which you get actually. So these are the outputs which you get after you actually define those x and your y. So these are the weights which you get after running a logistic regression. Right? So we can actually run this using your sklearn methods as well. In sklearn, you just need to import logistic regression. Right? So you can easily just import that particular class from sklearn. Just call in the method, create the object, and that is just fit and no predict. Right, so this is output. This is the output which you get after you pass maybe a C value as well. You just sort of this C is nothing but your learning rate, right? So you can set a learning rate as well. After you set a learning rate, when you run this, this is what you get. This is output which you get. Okay, guys. Then so we'll again meet in the next session where we'll just discuss on further topics. Thank you. So next we'll move on to interpretation of your logistic regression coefficients. Right. So previously I think you would have seen in the discussion on interpretation of linear regression coefficients. What we are basically seeing is, so since that being linear regression, say if you had a feature called feature 1, and with for that associated feature 1 you had a weight W1, right? So how do you basically interpret linear regression coefficient? Was keeping all other features fixed or constant, right? Unit increase in feature 1 would result in a W1 times increase. W1 increase. It's not W1 times. It will result in increase of your output, right, of your Y value by W1 times, right? So you consider, say, you built a model to predict how much bikes would get sold by month, by day, by hour, right, by different time frames. Say you have a feature called temperature. For that particular feature called temperature, you would have an associated weight of, say, 7, right? So how do you interpret that? Is, say, keeping all other features fixed, right? A unit increase in temperature would result in increase in number of bikes by 7. That's how you interpret it, right? All of that is in linear regression. Now, how do you basically interpret logistic regression coefficients, right? So one of the major advantages of your linear and logistic regression, right? In general, linear algorithms it's very highly interpretable. So when you actually compare this with maybe a random forest or maybe XGBoost, there is a bit of an issue in interpretation. Obviously, there are methods to interpret it. There are definitely methods, definitely are there. But in terms of ease of interpretation, say in terms of ease of interpretation, in terms of ease of explanation of this to maybe business, explain this to maybe business folks or people who run these operations, right? Linear algorithms are very straightforward. Right? So how do you interpret logistic regression coefficients? It's keeping all other weights or keeping all other features fixed, right? A unit increase in feature 1 is associated with X unit increase in log odds of your response, right? So here we talk in terms of log odds, right? Because this is a classification problem, so we talk in terms of log of odds. So what is log odds? Is nothing but you just take a log of your odds. Odds is nothing but, say, one very easy way to think of it is nothing but P by 1 minus P. Right? You have your probability, right? Probability, say it's say you have a bag where you have a box and you have a bunch of balls of different colors, and what is the probability of picking this ball of particular color is, say, if the number of balls are 5, say you're trying to put red color, which is 2 numbers, nothing but 2 by 5. So that is what is your probability. So odds is nothing but sort of reverse of it. So it's P by 1 minus P. So this is how you basically interpret your logistic regression coefficients. This is how logistic regression coefficients are interpreted. Again, very similar in term, very similar in a sense with linear regression, but the only thing over there, since that is a regression problem in linear regression, right? You do not, you just directly take direct units of weights. But here, what you do is you check for the log odds of your response. Right? Okay, then. Thank you, guys.